Now we want to move on to a property of matter that is very important in relation to our weather and climate, and that is a property of matter called specific heat or specific heat capacity. And specific heat or specific heat capacity is, by definition, the amount of heat, in this case, using Système International, joules, but in the old days it might have been calories or even BTUs, but the amount of heat, a quantitative amount, required to raise the temperature of 1 gram of any material 1 degree centigrade. Very exciting. And scientists over the last several hundred years, really probably in the last 100 or so, have quantified many, many materials. You can find catalogs of pretty much any material that humans know about, and someone will have figured out its specific heat capacity. How much heat do you have to add into the system, this mug, for instance, to get this ceramic to gain a single degree of temperature centigrade, a gram of that ceramic. And we see that some of the common materials that we are interested in are listed actually on the front page of your reference table. So this is right from the front page of your reference table on the top right. And you can see common materials: liquid water, solid water, water vapor, dry air. So this has to do with oceans and atmosphere. Then the surface of the earth, a common rock making up the majority of the ocean basins, basalt, and then granitic rock, or granite itself, which makes up much of the continental crust deep in the earth. Then common metals: iron, copper, and lead. And what we see is that the highest specific heat of all materials, and this is of all materials, is liquid water. It takes 4.18 joules for a 1 gram of liquid water to be heated 1 degree. So you have to add a lot of heat to get that temperature to rise. Whereas you see here, right below it, it's about half the amount of heat required to get ice to raise its temperature 1 degree. Therefore, it seems like it must be easier to melt ice than it is to boil water. It must take less heat. Maybe that explains why ice cream melts so fast. Water vapor is about the same as your ice. So it doesn't take much to heat up, or it takes half the amount as liquid water to heat up the water vapor in the air, for instance. Then dry air, half again. So over the desert, that air heats up at a rate of 1 joule for every gram of dry air that raises its temperature, or whose temperature rises 1 degree centigrade. Then we get into our solid earth. Basalt, 0.84. So obviously basalt must be heating up faster than liquid water by over 4 times. Granite, even less, is required to raise its temperature. So granite will heat up faster than basalt. Then iron, a metal, must be what we would call a good conductor of heat, because it heats up easily. You add very little heat, 0.45 joules to a gram of iron, and it rises 1 degree. Might explain why so many kitchen utensils, pots and pans, are made of iron, in the form of iron itself, cast iron, or steel, which has a little carbon added to it. Mostly iron. Then we have copper, elemental copper, which also heats up even faster. This can also be understood in the kitchen because many, many pots will have a bottom that has copper in it, so that the bottom of the pot heats up quickly and evenly. Finally, lead, which has this very low heat capacity. And we could also probably include mercury in this. Mercury has a very low heat capacity, one of the reasons it was initially put into thermometers. Nowadays, we don't put mercury in thermometers because it's toxic and when the thermometer breaks, it's not so good to have mercury around. So instead they use alcohol, which likewise has a very low specific heat. The only problem with alcohol is that it evaporates very easily, and I don't, maybe it's not as accurate, but it's pretty accurate. I'm not quite sure why it took them so long to dye alcohol and put it into thermometers, but for many years it was only mercury. So, specific heat capacity. For Earth science, this means that water heats up very slowly. This means the ocean heats up very slowly if it's cold from the winter. It means a Great Lake heats up slowly if it's cold from the winter. Likewise, it means that that same ocean cools down slowly when it was heated up in the summer, or the Great Lake cooling down slowly, or your pasta water heating slowly and holding that heat for quite a while. Because remember, our land is made up of those low specific heat capacity materials, granite or basalt and other minerals which have a low specific heat, land heats up quickly. You will find that rocks or the desert, the beach, gets very hot quickly. How many people have danced across the surface of a parking lot onto the beach with their feet burning up until finally they get their towel down on the sand and get relief. But if you stay too long at the beach and don't come prepared, that sand will cool down to the point where it's cold. And when you come back at the beach at night, you often wear more clothes than you had during the day, because that material that makes up the beach, the sand, which comes from rocks made of minerals, cools down with a low specific heat. And actually, likewise at the beach, you'll notice if you get into the water at night, it feels warm compared to the outside, where the air is being cooled by the land over it. Plants will also moderate the rate of the heating and cooling on land, and that's of course because plants are absorbing visible light and storing it themselves, either in the liquids inside, right? So the liquid inside the plant, and likewise using that energy in photosynthesis. So that moderates the temperature below. Likewise, many plants, taller trees, rainforests, create shade, and that shade also moderates the temperature of the land below the plants. What environment of the earth heats and cools most rapidly? Well, it's pretty obvious, but I won't tell you right away. Maybe a hint. It's almost like something you like after a big meal, or any meal. The desert. Now here's an interesting graph of our New York City. This is a temperature near the lower west side of Manhattan in the Hudson River, and it shows you what the minimum and maximum temperatures recorded through time have been for the water. And here we are in April, and you can see the minimum temperature in April is 3.9 degrees, maximum 10.7 degrees centigrade, or 41.7 and 48.5. Well, what would happen tomorrow if the temperature went up to 85 and you wanted to go swimming? You would find that the water is very cold because it's coming out of the winter, where it's slowly cooled and didn't receive enough heat from the sun to stay warm. And it takes, you can see, all the way till August for the ocean near New York City to reach its maximum temperature. So that swimming from, well, realistically May until sometime in July isn't that comfortable with a maximum temperature of only just below 70 degrees, far below your body temperature. So the water is cold. I should also point out that right now on April 2nd, the ocean water temperature in New York is actually at 47 degrees, just below the maximum, indicating that we are having a trend which is showing our averages going up as the earth is warming. So the ocean is warming as the earth is warming. So this is an interesting way to think about how slowly water responds to either gaining heat Because remember, the sun is at its maximum altitude, creating the most heat on the surface here in June, late June. So it's taken a while to heat up, and it doesn't even get much more than late June, right? It doesn't get much higher before it starts to lose heat end of August into September, October, November. And by the time we're in the November, the sun's angle is so low that it's just not getting warm anymore. So that's specific heat capacity, which we can calculate, and we will. Using specific heat capacity, the amount of heat generated in a system can be determined. This can be critical in many, many applications. When is the ocean going to be warm enough to swim in? We don't want your car overheating. Engineers in many mechanical systems has figured out just how much heat is being absorbed and released in order to understand better how a system will work. And for us, we're going to be calculating the amount of heat being absorbed by water and soil, and we're going to calculate it using this simple formula which says that the specific heat times the mass of a material times the change in temperature from a beginning moment in time to an ending moment in time. If we multiply those together and we cancel out the units, centigrade, gram, and centigrade, we will have an answer of how much heat in joules. So again, heat will equal the specific heat capacity of the material, say water, 4.18, times the mass, say 1 gram, times the temperature change, the rate of temperature change, delta. Say the change was 5 degrees. Then we would therefore multiply, I should say, 5 degrees times 1 times 4.18, and we would have an answer of 20.9 joules of heat absorbed by the water to raise it 1 degree, 1 gram. Okay, very simple. How much heat? And in chemistry, you're going to run into this in a different form where they call it Q equals MC times delta T, where Q is the heat, M is the mass of the water or the material, the specific heat is C of whatever material you're working with, and the delta T is the change in temperature of that material. So we'll be using this formula. Heat equals specific heat capacity of whatever material we're dealing with times the mass of the material times the rate, not the rate. Did I say rate? I shouldn't say rate. Just times delta T, the change in temperature from beginning to end. And as we said before, the grams and degrees centigrade cancel out of our answer, giving us joules, the unit of heat. And here again are the simple materials, common materials, and their specific heats that the reference table shares with you. And when we deal with soil, we use a number in here. Typically, soils are rated at about 0.79 joules per gram for every degree centigrade of temperature change. And I think with that, we'll stop and move on to our next subject in a little bit.